Vamos de nuevo para YouTube. Buenos días, bienvenidos a una presentación en el ciclo de seminarios. Les recordamos a los que están por YouTube que si quieren hacer No, ¿cuál es su pregunta? Está Marlon. ¿Está Marlon? ¿Está? Muy bien. No. ¿Cuál es esa? No, esta está muteada. Esta que es. Vieron que hay 4 computadoras a la vez, ¿no? No, el Zoom está muteado. Y la común. Ahí, hola. Bien. Bueno, nada, eso, que pueden hacer preguntas, pero que las hagan con tiempo porque tiene retroceso. Y Rosario, que está moderadora hoy, va a presentar a nuestro invitado.
Bueno, buenos días. Para mí es un gran gusto presentarles a Marlon. Y gracias, Marlon, porque le pedí que me hiciera una diapo introductoria, porque esto fue un poco rápido y improvisado, ¿no? Bueno, Marlon es el nuevo postdoc que se incorporó este año a la UIP. Él se incorporó hace exactamente un mes a la UIP. Y la forma más sencilla capaz de presentarlos a muchos de ustedes es que Marlon es la persona que está detrás del Pattern, que es el software, esa plataforma integral para análisis de datos proteómicos que muchos de ustedes probablemente hayan usado, y si usaron proteómica y no usaron Pattern es porque nosotros usamos Pattern, o sea, porque es la forma de análisis de datos proteómicos más utilizada hoy por hoy en nuestra unidad. Entonces, sin un poco de historia, les cuento que en realidad Marlon viene de la rama experimental, tiene una licenciatura en Ingeniería de Bioprocesos y Biotecnología de la Universidad de Positivo, en Curitiba, en Brasil, y entre 2018 y 2022 realizó su maestría y su doctorado. Fast track, Marlon. Ambos en el área de la proteómica computacional, más centrados en el análisis de datos proteómicos y en la generación de herramientas y estrategias para el análisis de datos proteómicos. Y ahora, solo con 28 años, está empezando su postdoc en la UNAM. Durante su doctorado, Marlon ganó varios premios en Fiocruz, en conferencias internacionales, y lo que más se destaca es eso que pusimos ahí, es que ya estando acá se enteró que su tesis, que se denomina Avances de la proteómica, nuevas tecnologías de adquisición de datos, herramientas y estrategias de análisis, fue seleccionada por Fiocruz Curitiba, fue nominada como representante de Fiocruz en el Premio Nacional Brasilero de las Tesis CAPES. Durante su doctorado, Marlon también recibió muchos apoyos, tuvo 2 becas de Yersin Calmet, una para venir acá, hizo una estadía de un mes, y otra para ir al laboratorio de Julia Chamot en París, todos en el área de la proteómica, y es coautor de 29 artículos de revistas arbitradas, más que sus años, y en particular se destaca su trabajo de tesis, donde es un primer autor en un Nature Protocols de Pattern Ciclo, que es esta herramienta que les comentaba que tanto utilizamos. Entonces, en este momento, Manu comienza a trabajar en nuestra unidad con un proyecto que es realmente desafiante y que trata de ir hacia uno de los problemas más importantes que tenemos en la proteómica hoy, que es las modificaciones posttraduccionales. Muchos de ellos ustedes lo habrán utilizado y saben que en esto nosotros encontramos solo lo que específicamente buscamos lo que sabemos, entonces estamos un poco ciegos, y la estrategia que va a plantear Marlon lo que va a tratar es de llenar ese gap y de tener herramientas para interrogar el proteoma y una cantidad de datos proteómicos de los cuales hoy no podemos extraer información. Yo conocí a Marlon hace mucho tiempo, cuando vino un primer curso de genómica en el instituto, y pasó de visita porque nosotros éramos colaboradores de Pablo. Y yo conozco a Marlon a través de su pasantía acá y la colaboración que tenemos con Pablo Carvalho, y les puedo decir que más allá de esta corta y destacada carrera científica, corta porque es joven, Marlon tiene características personales que para mí lo hacen especialmente importante en este instituto. Marlon es una persona que tiene una enorme capacidad de trabajo, tiene un compromiso con el trabajo que es impresionante, y a su vez es extremadamente generoso e interesado en colaborar. Por eso no me cabe duda que la incorporación de Marlon como postdoc va a tener un enorme impacto en nuestra unidad, en cómo nosotros analizamos datos y el tipo de proyectos que nos podemos plantear, pero también en el de todos ustedes si están interesados en hacer proteómica y colaborar con él, porque seguramente va a tener una excelente disposición a colaborar. Así que bienvenido Marlon, bienvenido a Marlon, porque Marlon no vino solo.
Okay. Hello everyone. Thank you, Jose, for the introduction. And so it's a pleasure to be here to present the research fellow project entitled Pinpoint Biological Relevant Protein Modifications by Mass Spectrometry and Vector Recognition under supervision of Dr. Rosario Duran. And as previously mentioned, Rosario, my thesis has been selected to award the CAPS thesis presented by Fiocruz. And I developed two two main softwares in this thesis principle. And the pattern map is published in Nature Protocols and the diagonal maps. Before we start about the talking about the data analysis, we need some basic concepts of proteomics. For example, here I bring the proteomics workflow. How can we generate our data? So first, we have our sample provided from cell, tissue, microorganisms, and others. And then we extract these proteins from these tissues, or the things that contain proteins. And then we digest these proteins into a peptide. And then we analyze from mass spectrometry. Before that, we acquired a lot of data. These information that we have, this contained here, for example, per run, we generate around 150,000 mass spectra. So this is a lot of information because the one run on. Imagine when we want to compare one biological condition to another, that we have three biological conditions with two technical replicates. So we expand this a millions of thousands spectra. In this spectra, we contain the various information about the peptide, but not only the peptide. As Rosario mentioned, the relevant modifications there's in these spectra. There we have the information, the post-translational modifications. And then, how can we generate this information in the mass spectrometer? The most common acquisition that you use to provide the data for mass spec is called data-dependent acquisition. And how it works. Here we have the chromatography, and we select some time point here in the chromatography that we call the MS1 spectrum. And what is the MS1 spectrum? The MS1 spectrum will have all the ions elute in this time point from the chromatography. And then the mass spectrometry select the most intense ions. For example, here we have this precursor ion that generates this spectra MS2. So here we have the fragmented peptide, in this case the ion, and then another fragmentation. And this cycle occur during the all chromatography. So the mass select another time point here. We have MS1 spectra, fragment in MS2, 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 and we did all again, right? So here, this information that you use to analyze our data. But the fragmentation is not so simple because we have different types of fragmentation. But the most common fragmentation that we generate our data is B and Y series. What is the BY series? Here we have a chain of the amino acids. And here we have the amino group, the side chain, and carbox group, right? And here we have the peptide bond. The fragmentations occur directly in this bond. And here we have the another amino acid, this carbox side chain, carbox group, and another fragmentation in the peptide bond. This facilitates us to analyze our data because we fragmented the chain into amino acid, not without amino group or carbox group, as we have the another fragmentation. So I bring it to here an illustrative how can generate this fragmentation. So inside of the mass spectrometry, we have a gas, for example, like nitrogen, that these molecules collide with the gas. And then when we collide this sequence, for example, we fragment it. And here we have a part, the amino acids, this is another. So here we have the B series and the Y series. Here we have another fragmentation, so the B series and Y series, and this and this. So here we have our experimental spectrum. And that is here we have the information of the sequence amino acid and cross-translation modifications that the amino acid contains. So for analyze this data, we have three principal paradigms for peptide identification: peptide spectrum matching, open search, and de novo sequence. So I'm going to start the talk about peptide spectrum matching. So once you have experimental spectrum, here I illustrate the experimental spectrum with a mass 928, and for example, I don't know, this is from Escherichia coli, right? And then we downloaded the database from the UniProt or any CBI, the sequence of proteins in FASTA format, provide this organism, and then we digest this database as we did in the wet lab. We use, for example, trypsin. So we use the same rule here to fragment the sequence of protein into peptides, in this case, like a trypsin. And then we generate for each sequence which contains this mass, we generate a theoretical spectrum, right? And how can we generate a theoretical spectrum? So here I simplify how can we generate, only use the B series, because as you know, the B series is forward. If we use the Y series, you need to reverse. But here is only to simplify. For example, we have the sequence peptide K, and then to generate this, we know the amino acid mass, right? And so what we can do is sum. So we put here the mass of P, the P plus E is another P, P plus E plus P is another one, and so on. And then we generate our theoretical spectrum. So now here, what we provide to analyze this data, we correlate this spectrum with another one. So how can we do it? Like this. So as you can see here, we don't have a perfect matching, right? And so this received one score. For example, here, we call the cross correlation because this is the correlation, right? And 0.3. We have a little bit correlation with theoretical spectrum and experimental spectrum. And then we have another sequence. This is perfect correlation, so receive the best score. So score equals 1. And the another one, another candidate, this is not so good. So the score is so bad, right? And then when we have the cross correlation here, we select the best score to annotate the spectrum. So in this case, we have the peptide K. This is correspond to this experimental spectrum. So here now we have one identification. What is the limitation of this technique? As what I mentioned, we need to insert in the search engine a post-translation modification that we want to see, for example. If I want to see post-translation modification here, for example, phosphorylation, I need to insert this information in the tool. So now imagine, if I want to see the phosphorylation here, I need to create. I will duplicate my database. So imagine if I have 1 million sequence here, now with only one with post-translation modification, now I have 2 millions, all right? Imagine if I put 5, 10 post-translation modification. This increases a lot. And then Our filtering is based on false discovery rate. So the false discovery rate, if the database is so huge, we introduce a false positive in our analysis. And then, so imagine if 1% in false discovery rate, if you have 100 proteins, this is missing, right? And then if we have 1,000, then in this 100, right? So that's why this is a limitation of this technique. So we need to know what we want. In this paradigm inside of the pattern lab for proteomics. So the pattern lab, we have this module that contains peptide spectrum matching that we use to identify the sequence of peptides. We have another modules for filtering, for quantification, label free and label. We have another modules here for visualize our data, like Buzius, that we saw this like a PCA, default is a volcano plots, and the Venn diagram that you want to compare by one biological condition to another, clustergram that use a vertical clustering here, and trend quest if you have a time point series, time point experiment, right? And the another tools here to generate a database, to visualize our data, and convert the data stream. So the pattern lab is a proteomic pipeline that you can perform the identification and quantification and have a lot of modules that you can help to interpret the data. So the another paradigm is called open search. So the open search is very similar to PSM. But now we have the experimental spectra with this mess, right? And now the open search, what we doing here, we create a window that you can perform the search between 500 to 1,500. And this is a limit that we impose in the software. For example, if I have one modification with 600, I lose it here if you use this methodology. Because as the same in the PSM, we download the database, we use the sequence of this database, and we create the sequence with some modifications, but that respect this limitation in range of the mass. And here, for example, we have the sequence without modification, the sequence with glycosylation, and the another one we have here, the glycosylation and amino acid substitution here. So now, in this case, this technique is limited to two up to modifications. If we, for example, try to identify the third modification probably containing your amino acid, you cannot find it. And then the same paradigm. So we generate the theoretical spectrum for each one of these modifications that's combined in this range of mass. And the best score, we annotated the spectrum. So here we have another identification. So we imagine we increase a lot your database here, and we cannot provide a search in a notebook like pattern. We need a server because here we spent a lot of memory to generate this theoretical spectrum. So one of the example of tools that use this methodology is MS Fragger, that inside the Frag file. And the third one is the de novo sequence. The de novo sequence, here we don't use any information about the database because the de novo sequence, we use only the difference between peaks to try to identify the amino acids. This tool is important that when we want to try to find some mutations in your sequence. So here, for example, the difference peaks between this and this is corresponding P. This is another one, P and E. So we try to combine here between different masses between peaks to try to find some amino acids. So this paradigm, in this case, we don't use any information about the database. In the PSM we need, and the open search too. And the example of tools that you can provide us this information is on our cloud computers. And now we have a new way to analyze our data. It's called diagonal mass. So the motivation to develop the diagonal mass is because 75%, as published in this paper, 75% of spectra remain unidentified. So the data that we produce today, only 25% we have the information, and we spent a lot of information that because this limitation of this technique, we don't have information about post-translation modification or mutations. All right. And the diagonal mass is based on clustering. So here, I will exemplify with this, but the diagonal mass don't use any information about database, only the information in spectra and how it works. For example, here we have the condition A and condition B. And here we have a spectra that exclusive for the A, and this spectra that exclusive the B. And here we have the spectra are shared between these both biological conditions. And so diagonal mass verify if the spectra contain similarity and create a cluster. Just like this. All right. So in this case, as I mentioned, here we have here's exclusive cluster, this is another one, and here we share this information. But this information is only based on compare one spectrum to another and generate a cluster. And so the general aims of the research fellow project is generate a new tools to interrogate proteomics data in a new ways to overcome a firm limitation. See?
So what is A and B?
Okay. Here we have a biological condition A, for example, healthy, and here I have one disease. All right. And then this is the only information that they contain.
Okay.
And then the two check the spectra here are similar. But when you put all together, they can check here. So in this case, this cluster, these spectra are similar, but this is exclusive to condition B.
Okay.
And this exclusive to condition A, and these spectra are shared between these clusters. All right. So the general aims of the research project is to generate a new tools to identify peptides not including the database and that contains unexpected PTMs, and use the framework here to project focus on identification and antibiotic resistance. And the third one is the output of this proposal have a broad immediate applicability, right? Which will be by contributing with the proteomic stack for that. So the first specific aims is improve the diagonal mass. So interfacing the diagonal mass with established academic identifications like pattern lab, rapid de novo, and mass failure. Why? Because the diagonal mass, we have only the information in the spectrum without any identification. So now we want to know what is the sequence contained is in this spectrum. So that's why we use all these three paradigms to put together in the diagonal mass. So the first aim is already published. And here, as you can see here, if we use the three paradigms, we can expand a little bit information. So for example, PLV is representing the red circle here. So we have a lot of information, the identification, the sequence of the pattern. So when you use another paradigm here is the Frag pipe that they call the open search, that you try to verify if it contains some modifications, post-translation modification. We have a little bit more. In de novo is based on the de novo sequence to try to identify if it contains some modifications. Right? This is very important because each paradigm contains exclusive things that we cannot see if I spend time only in one tool, right? And this is very important, but this graph is most very important than compare this. Why? Because here we annotated the clusters. with the information provided from this paradigm. And as you can see here, more than 50% of the information is remaining unidentified. This is corroborated with this paper, that 75% remain unidentified spectrum. But why this is continuously losing the information in this part of the information of your data? This is why, because if we contain some unexpected PTMs, we cannot identify it because the information is not in the database. Is not because we try to hear new things. For example, probably here we have a lot of biomarkers for biological condition, right? So even if we use the three paradigms, we continue losing the information about your data. And now, with this motivation that you saw, we will create an identification belief propagation network. This is a new model that we will input in the diagrams that we try to shine in the light of proteomics dark matter. This is the PTMs, spatial modification. And how the identification belief propagation works. So here we have on spectrum that we already know we have the best score, and we try to find some patterns to try to recognize in another spectrum that cannot identify by the, for example, PSM or certain denosities. And what we did here, if only to see this spectrum, you can see here we have a pattern here, right? And this pattern represents these three amino acids. So here we annotated this spectrum with this information. And then we shift the spectrum to the left and to the right to try to find another pattern. But here, when you can see here, this is, we have additional modification here. This is not correspond only to a T amino acid, right? T amino acid plus anything, right? Because of something that increased the mass. So here we can saw another modification. And how can we verify, well, this is a correct peptide? How can we saw if this is a correct peptide and is not another one? This is because we can saw another pattern here is a representative in this spectrum. And so now we have the information about this spectrum that with the information as the same, but here we have some modification. And that is we'll do in all the database that we generated. So the circles represent the clusters. So here with the bar chart here represent a spectrum, and the green represent this spectrum is identified. And then, as I mentioned, we correlate this, for example, this spectrum to this that we remain unidentified. This spectrum with this, and this spectrum with this. Because here we have information that these three spectra is the same pattern in the cluster, right? And now we doing this with another information here in the cluster. And we saw here the information are similar, but as I represented here, here we have some modifications, some additional mass. So for example, here we have N-acetylglutaminic neuraminic acid. So here is a glycosylation. So here we know now we have the information of peptide as the same plus cross-translation modification, right? And then we not only to do this one cluster, we try to find another cluster that the peptides as the same, and then have another cross-translation modification like this. And now we found another modification, Manos, right? But remember, the limitation of the techniques that we have is limited to two modifications, all right? And now we have the sequence with each one contains one modification. So now we can try to find another cluster in here. I don't know if I can move
Yes.
this part. Yes.
You can hide them
Hide them.
together in more. If the three dots are more, hide floating meeting.
So now we know we have the information. Remember that we have the information this. If has the same peptide with this plus post-translation modification. This is another one with another post-translation modification. And now we try to find some post-translation modification here. Yes.
Okay.
And now we saw here that we have one post-translation modification. But it's true, this peptide contains two post-translation modifications. And okay, so Mark, we already have the tools to do this, right? But now this cluster, we can propagate the information to another one cluster that probably contains the third modification or one modification. This is unexpected. So this is our methodology. This is our strategy that we use in the database generated from the information. So remember, the more than 50% of the information we losing. If we use this methodology, we can increase the difficulty because here we have unbiased information, the PTM, only based on mass. So in this case, we can find another modification that is not in the database. With, for example, if you use the Unimod, there is listed only 1,500 post-translation modification, but you know, in the nature we have more than this. And so this methodology can increase to try to find some another post-translation modifications. And the third aim is the pinpoint biological relevant protein modification by mass spectrometry. Investigate the relevance correlate with resistant mechanisms by using the proteomics approach. The proteomic approach is identification belief propagation network.
Marlon,
See?
can I ask for the previous?
See, yes.
Just one thing, you're talking about sugars.
Mm-hmm.
So one thing that comes to, do you use in this, what's again the name of propagation relief?
Yes, it is
What's the name?
identification belief propagation
Propagation
network.
network. Do you use within it some kind of prior knowledge
Mm-hmm.
about biochemistry, biochemical,
Mm-hmm.
biochemical prior knowledge?
Mm-hmm.
Because what I'm thinking is that in sugars and monosaccharides, you
Mm-hmm.
have many of them have this same mass,
Yes.
right?
Mm-hmm.
So how do you know it's mannose
Yeah.
and not a glucose and et cetera, or different variants of neurominic acid and so on and so forth? Do you include some kind of knowledge about biochemistry to better guess?
Mm-hmm. Yes. First, we doing this with unbiased database.
Right.
We only to try to find mass.
Right.
And then we use the information already published to try to incorporate this to help us to analyze, for example, the glycosylation is a huge change. So the fragmentations when occurs in the amino acids, we have a different peaks inside of the mass spectrum, right?
Right.
And so in this case, with the shift of mass, we try to correlate this information to some glycosylation. Okay.
So now you're thinking about. I was starting from the very simple example that you gave, which is useful. It could be biologically relevant because some glycosylations include just one sugar.
Yes.
But of course, many of them, probably the most you want to know about are oligosaccharides.
Yes.
So now I'm more confused, I think.
Ale, probably the results here won't be mannose, just pentose, hexose. And if you system where you know that you start with.
That's the prime knowledge.
Or,
So you
the-
need that. You need some kind of,
Which kind of flows?
and then if you have
Because at least
oligo,
there is mass.
and then oligo,
Mhm.
then you can also do the same in a way.
Mhm.
Probably several of them are really mass defined.
Mhm.
So you can say this is a high mannose type or a complex.
But for example, if your sample that you already know that you have mannose sample, the software, let's start here without any modification because we are already inserting the software that I know this is a mannose, right?
Yeah.
So the network starting from this point,
Right,
and then we can
Of course.
increase the information.
exactly.
All right. So if you already have for the software, the data analysis, you facilitated to us. All right.
Thank you.
Just curiosity about the theoretical background for this.
Mhm.
When you implement this clustering, you use some specific function to optimize the clustering because sometimes people is concerned about the using modularity, for example.
Mhm.
Function to
Yes, we use the algorithm in the background of the diagram is hierarchical cluster.
Okay.
This is already published with different groups that hierarchical clustering produce that we call a purity cluster. In this case, for example, as I represented here, if these clusters contain, for example, imagine that these clusters is only one spectrum I identified. Based on this algorithm, we saw this another one, the another spectrum as the same, but because of the another methodology that I mentioned here, the paradigms here, sometimes the score is not so good to pass the false discovery rate. And then when we saw here the sequences, for example, Marlon sequence here, we know in this cluster, this sequence is Marlon clusters, Marlon sequence, in this cluster, this third spectrum represent the Marlon clusters. So this is a purified cluster that I mentioned. So this corroborates all the information because if this algorithm is not so pure, imagine if I have here Marlon sequence, Rosario here, we lose all this information. So that's why we use this type of algorithm to improve our information about the cluster.
Mano, one question, because I think what Alejandro said is an important point for the outputs, for the people who is going to see the data. So you put Manos there because you have a delta mass, and then you cross-link it with the Unimod, and then it says Manos.
Yes.
But it says other things.
Yeah, sure.
So you're going to include everything there,
Yes.
so you will know that there's some
Yes, we
kind of a lot of possibilities or something like that.
Yeah,
It's,
yes,
it's
yes.
going to consider that.
Yes, we consider because this is a
Yeah,
network. Increase. And then, for example, we know how this is fragmented in the mass spectrum. Then we can generate a theoretical spectrum of this fragmentation and try to insert to validate information.
I didn't understand that.
No?
No.
For example, we know this fragmentation occurred, for example, with some space, right?
Yeah.
And then we can generate this and doing like a PSN to try to corroborate, not to show to him, we have some modification like this. We have this pattern that corroborate information.
Okay.
And then the third one is using all these tools to investigate the resistance mechanisms with the microorganisms. So the recently published in the scientific community shows the cross-translation modification for example, here in this paper, characterization of phosphorylation modifications, modifying multi-drug pump review that an expected link between glucosylation and antimicrobial resistance. So this is another important topic that correlate the post-translation modifications with biomarkers, with resistance mechanisms. And then we hear another review that is related with post-translation modification with the microorganism. And all these tools we're gonna use here in this project, proteomic strategy for diagnosis of bacterial infections and identification into antibiotic resistant markers, because we receive here the samples from the hospital, and then we use all this spectrum that we already know, the information about the microorganisms that we already identified, to create this knowledge base to try to identify, to correlate this post-translation modification with this resistance, because the microorganism in the hospital contains resistance. And this is unpublished results, but I would like to share with us, because here in the green dots, like this, okay. This is a Acinetobacter baumannii resistant apomyxin, right? And we have here the another Acinetobacter without resistance. And when you use the traditional paradigms to try to identify, these proteomes are very similar. And this information that we try to separate here is based on the database.
What are you plotting?
Sorry?
What is the plot?
This is a PC based on proteins. Answer?
It's searched by PSM.
PSM, all right. Here we use the pattern. And this paradigm is based on you have a database, we try to do, we're doing the PSM, and here is not separable.
Right.
Okay.
What each point there is what?
Each point, this is one bacteria.
Proteome.
Oh,
One proteome.
good.
Okay.
Good.
Okay. This dot, each point, this represents one proteome. All right.
And then you do principal.
Principal component analysis. Yes. But if you use the PSM peptide spectrum matching, we cannot distinguish one bacteria than another.
Mm-hmm.
But when you use a clustering method, like in the diagrams, it's clear here. We can separate the non-resistance with the resistance bacteria. And here, we didn't apply any filter here. This information is the raw. We get the information from mass spectrometry, inserting the tool, and this is separated. We click plots. Here we don't have any filtering. So this is so important to use a clustering method, because the clustering method is unbiased of the database. Only perform clustering. So the diagonal mass see things that you cannot see. And that is so powerful. This is why diagonal mass is so powerful. They separate the resistant bacteria and then another one.
Is that enough? I mean, you know which ones are
Mhm.
resistant and not in this case,
Yes.
because you're learning. But that doesn't seem to be too good at clustering, right?
Yes.
It is.
Yes, this is a good
You
question.
can tell
Here.
one cluster from the other.
Yes. Here we have one group. This is represent a known representative.
Yeah.
Here, no.
Yeah.
That is so impressive to use this methodology, because some more than 50% of your data that you cannot see anything, the diagonal mass can see, and then we use this to separate this information instead of the PSM that the information is based on the database, we cannot distinguish. So this is so relevant to use this information, this analysis to provide us information on and pinpoint the relevant modification in our data sets.
One question
See.
about this last one.
Mhm.
So you can classify there, but you are not going to use this to put a new bacteria and say it's this or this.
Yes.
It's
no.
no, or are you going to? Because I think that no, I don't think so yet. Because this what gives you is the idea that all the spectra that haven't been identified by database search have an information that allows you to a better classification. No?
No, here without information.
Yes, if you take all the spectra instead of only those identified by database search, you can classify correctly.
Yes.
But
But
can
here,
you do that? No. So all this information you are throwing, it has a lot of value.
Yeah,
The
that's,
point is, I'm not sure you're going to classify. You have to.
well, the idea is,
yes,
I mean,
they,
what I would say is that that's incredibly promising.
Mhm.
It does show what you say that it's, but it must be improved in terms of what I see there naively is a continuum
Mhm.
among the two clusters.
Mhm.
Of course, if you go to the extremes, you're very confident, but what about those middle,
Okay, here,
are they resistant or
okay,
not? And
but
I
here,
would believe any of,
here.
that was my point.
No, but this is raw data. If you increase some filters here,
Of course.
these clusterings, we separate more and more and more and more. All right?
No, what?
No. Because, for example, here we can put we only use the database cluster. So in this case, try to find some cluster on the data. For example, if we input here, I want to see in this biological condition, for example, a minimum, the spectra in the cluster, we have, for example, a minimum items in cluster, for example, is 3. With increase here, the filtering, this data set, we separate more this information because now we will apply a filtering. And here, without any filtering, we are already capable to separate this information. Right? Answer or question?
We can discuss that. Oh, thank you. No, it's amazing. I mean, it's clear the point that there's a lot of information. that
So,
you're picking
yes,
up.
we want to compare here. If you use the traditional methodology, you cannot
That's-
distinguish. But in
That's
clustering,
clear,
yes.
clear. Very nice.
I mean, also, sorry, if you have that labeled data, if you having that those labeled data,
Yeah,
you can precisely quantify your error rate with quantifying.
Yes.
yeah,
And I think
yeah.
the most promising thing here, Alejandro, is that when you go into this data, you can have cluster of spectra that are exclusive of resistant and cluster of spectra that are exclusive on non-resistant.
Focus on those.
And then you can focus on that. This is a general.
That's a different, yeah, it depends. That's why it depends on what you want to do with it.
Yes.
As you explained it, maybe it's, I thought it was mostly because you want to do diagnostics,
Mhm.
which is, I think, one of the goals, right?
Yes, right.
That's one thing.
Mhm.
So in that sense, it's improvable.
Mhm.
But of course, what Rosalie says is another thing, is that you already know, and you want to do fundamental research in trying to go and pick better pick,
Mhm.
subproteomes or focus on proteins that are really important for that resistance.
Mhm.
And that I'm absolutely agree already. It's done.
Mhm.
You can go for diagnostics.
No.
It's not
Yes.
clear and what.
No. For diagnosis is is another part.
Yeah, but as Marlon said, the first thing is to try to map PTMs on
That
this
works.
group of spectra that allow it to separate and not.
Yes.
Great.
Yes, we separated. Here we have, for example, the excluded clusters that we can investigate. Good. Yes.
Yeah, it's amazing. Did he finish? Did he finish?
Yes, now I will finish. Thank you.
Great. And so what you're saying is that this biomedical tool can be used to nourish, let's say, the model database to identify, to do some diagnosis, as the doctor said. Is that the endpoint, right? Okay, to identify that gap that we have in the database that are not identifiable.
Yes, we try to identify this. We're using the, I believe, propagation network because here, for example, we have the data and we try to here. Most of the information we still losing here. And that is so why important to use this methodology based on clustering to identify. Answer?
Yes.
¿Alguna otra pregunta? ¿A ti?
You're going to stay a couple of years here. No, so to get you impresionante, chico.
Sí.
So, no. One curiosity and another curiosity.
Okay.
With the interfacing stuff, you're interfacing your software with proprietary software, right?
It's free software.
Oh, it's free.
Yeah, it's free academics, yes.
Okay, cool, great.
Yeah.
So no problem there.
We it's easily trusted when you use open source.
Right. So,
Because-
so-
Yes.
no problem there. Now, but for the when one is exploring one system, I agree that we all know that the more you know about your system, the more you know about how taking care of your samples, the best are going to results to be okay. But imagine you're looking for transcription factors, two which are very similar, and one which has a potent effect with a very transient modification, and another which has one potent effect the other way, but with a stable modification. But you know that you perhaps have 20 molecules. That's all. Totally the same would do all the job. So, what kind of calibration would you recommend as those kind of cases? Or is it? How do you calibrate to focus on specific questions? That would be the general question.
Okay. For example, if you have some postulation modification specific, right?
Yeah.
Please understand it like this.
Yes.
Yes, for example. We cannot calibrate here. You mentioned here the I believe this, right? This algorithm.
Yeah.
Yes, you mentioned, right? In this case, we not calibrate for one of those population modifications. But here we have this is unbiased. So, for example, you know that you have like manos, for example. We know that you try to find manos, but in this algorithm we explore more than manos because the convention paradigms already did. If you want to see manos, you can include this in your database and try to find. But here, help us to shine on the light of their matters to find another possibility. That's it. Yes.
Yes, sort of, but you'll be around. So.
¿Alguna otra pregunta? Sí.
I'm curious, after your tennis clustering, it's available, you are able to create some rank protein just to see which one contribute more to this clustering or not. You can tune that.
Yes, we will create one score to correlate. So, for example, here is clusters in here of these, so are more correlated. This is another to try to, because this is helps the user to identify if these modifications occur or not.
Which spectrum is more relevant to contribute to this clustering?
Yes.
And you also showed only two components. So
but you can insert one score to help.
Probably, yeah.
Is there some limit imposed to the propagation through the network by the fault scoring rate? How do you manage?
No, the fault score rate here in this case we don't have fault score rate. The previous results that we insert in the database we have the fault score rate, but here no, because here we.
But when you match one cluster with this cluster with that one, you do that matching with some score.
Yes,
And
yes.
That's I understand it will be one.
Yes, but for example, yeah, we have probably.
And then if there's no limit to propagate through the network, accumulating scores that are not one.
Yes, we can insert the limit, but what we put here is like the null sequence. We don't have a limit here in this case. Of course, if you saw one cluster here, 100,000, one other approximation modification with 5,000 Daltons, this is this approximation modification cannot, because you combine a lot of approximation modification that is not true. But here in this case, we try to, as mentioned here, try to doing here the correlate approximation modification. So in this case, we use here, I don't know, phosphorylation. We know this is the difference of how many. So 80, the mass, the difference here, we know here we have a phosphorylation modification. Not so much. We increase a lot with that.
Una otra pregunta para Marlon. So we have one YouTube, Matías Machado, who is saying it's a very nice presentation. If there is any methods, if these methods are very computational expensive.
Yes and no. Because the diagonal mass, because we clustering our data. So when we cluster our data, we reduce a lot of the information. And imagine so in the PSM search that we use in the notebooks, you can provide the PSM search in the notebooks, right? And we have a millions of thousands spectros. When you cluster here, we reduce the data in a half and third, right? So that's why this is not so computational effective cost. So they can reduce a lot.
Cecilia. Asking a question about when you use this tool that diagnosis bacteria, no? If you compare.
Yeah, this is not a diagnosis.
No. Yeah, to have a method to allow you to do that. When you compare metagenomic with proteomic, what is the advantage of proteomics? It's cheaper, it's faster, it's more precise. I don't know anything about metagenomics either. That's for curiosity.
The good things, yes, I mentioned here, is the phosphorylation modification. The phosphorylation modifications occurs at protein level. When we use the technology based on proteins like mass spectrometry and peptide level phosphorylation modification, we get everything. In the yes, the metagenomics, these informations we do not contain. So the PTMs are so relevant because we have the information in the protein level.
Just a quick comment to Cecilia, which is, I think, a good question, is that maybe, and it's not that usual nowadays, all this kind of discussion comes back to mechanisms, how things work. Both proteomics and genomics and metagenomics are very biased today because of the power of application to biomarkers, to marking, to predicting. And they do it very well. I think metagenomics is much cheaper,
yes,
much easier than this. And you will get many things because many of the resistance mechanisms don't happen because of PTM. But many others, yes. So you will be missing some and some. And in the end of the story, maybe it's interesting to also know how these bacteria are resistant. So in that sense, all these techniques will just be the beginning of a research to understand. And maybe it has nothing to do neither with the genes nor with the.
Yes.
So there are many
I
things
think
happening.
this is a complementary. For example, if you have this metagenomics of this protein, you can use your database to insert, for example, in the pattern, you can provide the PSM search.
Yeah.
So now we have, for example, some mutation, yes, and then we can use the diagnose to increase our information to verify. So I think this technology is not competitive, but it's cooperative, right?
¿Alguna otra preguntita? Vale. Thank you. Gracias. Okay. Quick question. Shall we keep it target? So we have the video now on YouTube. We can keep it private or public. This is the one. Okay.
For me?
Just wanted to